morning friends. We shall continue our discussions on IIR filter. If you remember, yesterday we were discussing about Chebyshev filter. Now, we can write the Chebyshev function in the analog domain as 1 by 1 plus epsilon squared Cn squared, okay, omega s by omega p. This is a function of omega s by omega p. This is in terms of stop band and pass band ratio. So, this can be written as 1 by 1 plus epsilon squared cos, as I had mentioned yesterday, cos n cos inverse omega for omega less than 1, and it is cos n cos inverse omega for omega greater than 1, and both of them generate the same polynomial functions. So, cos n cos inverse omega s by omega p whole squared Cn square means this is Cn, and that is equal to 1 by s squared, where if you remember we had mentioned in our earlier characteristics the quantities A and epsilon. I will just refer back to the earlier notes. So, this was given as 1 by A, and this was the tolerance in the pass band. Okay. So, we will refer to the same quantity A, and that will be equal to 1 by S square when it is in the stop band. Okay. So, S squared minus 1 by epsilon squared is equal to cos n cos inverse omega s by omega p, which gives me n equal to cos inverse root over of s squared minus 1 by epsilon divided by cos inverse omega s by omega p. Okay. So, this is how you determine the value of n, which is equal to cos inverse 1 by k 1. We defined the two quantities k 1 and k. So, it comes like this. So, the polynomials can be framed, we have to get the roots. So, say gamma equal to, basically the Chebyshev roots will be lying on an ellipse. Okay. So, if you are given epsilon, then you can write this 1 plus epsilon squared plus 1 divided by epsilon to the power 1 by n zeta equal to gamma squared plus 1 by gamma, and there are two different entities. It becomes a little difficult. I will call it 1 and 2 to distinguish, because our handwritings are not matching with the prints. Roots will be p k equal to sigma k plus j omega k. These are the roots, kth root. So, sigma k is given by minus omega p times theta 1 sin 2k minus 1 into pi by 2n, okay, and omega k is equal to omega p the 2 cosine 2k minus 1 into pi by 2n. Okay. Basically, they represent major axis and minor axis of the ellipse, omega p times this. There are other ways of looking at these Chebyshev polynomials. There are many books where they refer to the direct design tables, and we will discuss that at a later stage. Let us come back to what we were discussing yesterday. I had given you a small problem to try at home. Did you try that? You can see f t we are considering in the discretized form as f s t. Okay. I can write say sample values of a continuous function as f t multiplied by a series of delta functions at regular intervals of capital T. T is the sampling time, okay, k varying from 0 to infinity. So, if this is your f t, we are multiplying by delta functions. So, these are the sampled values. So, delta functions of unit magnitude at regular intervals, that will give me f k t as the weightage of that delta function. I can write like this. Now, Laplace transform of delta t minus k t is e to the power minus s k t, okay, summation, is it not? This is a shifted function, shifted impulse and series of shifted impulse. So, it will be giving me a summation over k this function. Okay. So, if I call the Laplace transform as f subscript s, this will be Laplace transform of this, okay, which will be f k t e to the power minus s k t. Do you all agree? So, this is nothing but Z transform evaluated at Z is equal to e to the power s t basically, is it not? This is by definition Z transform. If I substitute for e to the power s t Z, then this becomes Z transform. So, f s s will be 1 by t summation. This is a proof that I asked you to try out. Okay. Let me write in s omega s t, instead of that I will write capital omega s. This is the sampling frequency in the analog domain. We will do that. That means, whatever value of s you are having, you replace s by s plus j n omega s, and n varying from minus infinity to plus infinity. Okay. This is what we have got. Basically, this is the situation from where we are getting aliasing, is not? See, let f s be a 1 by s plus s 1 plus A2 by S plus S2 and so on. Let us consider only one of them. We are trying to find out what will be Fs by Fss. We have seen Fss will be F, the original F, S replaced by S plus this with an average. So, we want to derive this relation. So, let us consider only the first term. Okay. So, A1 by S plus S1, what is its corresponding time domain response? If I call it F1t, that is equal to A1 into e to the power minus S1t, agreed. So, F S1 S, that means corresponding to this, what will be Fs? It will be A times A1 times discretized version of this. If I take e to the power minus S1 kt, e to the power minus S kt, do you agree? Is that all right? Because this is e to the power minus S1 t, we are taking Laplace transform of the discrete version of this. Mind you, S1 k t, I have just put t equal to k t. So, these are the magnitudes and this is the just in the previous step we have done f k t into e to the power minus S k t. So, what is f k t? The magnitude of the function, that is e to the power minus S1 k t, is it not? Because the response due to this is e to the power minus S1 t that we have seen. So, if I discretize it k t, this is the specific value at that point. So, this summation will give me A1 by 1 minus e to the power minus S plus S1 into t. Is it all right? So, a term like A by S plus S1 will give me correspondingly here A by 1 minus e to the power minus S plus S1 into t for the sampled function. So, what are the roots of this? What are the poles of this? That means corresponding to a pole at S equal to minus S1, the set of poles that will be generated here will be the poles for the discretized function. So, we are trying to find out the poles of this. So, that means equate this to 0. So, e to the power minus S plus S1 into t is equal to 1, all right, is equal to e to the power j 2 pi n. Okay. So, equate this to, so S plus S1 is basically j 2 pi n. Actually plus or minus is immaterial because I can always take negative integers also, 2 pi n by t, okay, and okay, let me put it minus, then S is equal to minus S1 minus, it can be plus or minus, j 2 pi by t is omega sample, omega s into n, all right. So, S equal to minus S1, the root at minus S1 will generate minus S1 minus or plus n times j omega s. What does it mean? That means, in the original time domain, if there is a pole here, then for the discretized version, this is for the continuous function, then for the discretized version in the S domain, you will have poles, an infinite number of such poles at regular intervals of omega s. Okay. Now, the effect of when I am traveling along this, you traverse the entire omega s, the imaginary axis. So, if I go along this at any point, what is the amplitude? I compute the amplitude by taking the zeros, distances of zeros and poles. Suppose there are zeros also. So, there will be zeros correspondingly multiplied here. We are concentrating on one single pole. There can be large number of poles in the family, large number of poles and zeros for the original one. So, the entire set will be repeated. Now, at any point, if I want to find out the magnitude in the discrete domain, if I want to find out the magnitude of the function, then all such distances of poles and zeros will have to be taken. But then these distances will also influence, these distances will also influence, all right. So, at any frequency, if you consider the distances of poles and zeros and take the ratio of the products, that will decide the magnitude. And if you do not eliminate the influence of these, that means they have to be widely separated, okay. They have to be widely separated. That means this omega s should be very, very large, that means sampling frequency should be large, otherwise there will be aliasing. So, this is the logic for having omega s very large. Now, we will take up some examples. Before we go there was one question raised after the class, that is, can we avoid, we are giving examples of impulse invariance and step invariance. For step invariance, we found there are two delay elements, all right. Is it necessary to have two delay elements? So, it is not. So, suppose you have a function say h z, I will take a simple biquad b0 plus b1 z inverse plus b2 z to the power minus 2 sorry. Okay. What will be the structure for this kind of function? Now, I can segregate this into 1 plus a1 z inverse plus a2 z to the power minus 2 into another part b0 plus b1 z inverse plus b2 z to the power minus 2. Okay. If I consider this as part 1, okay, then I will have, suppose x n is the input, z inverse, then I can have minus a1, similarly minus a2, another delay block z inverse, and they are summated, then again they are summated here. Okay. Now, summation we normally note by a small circle, and even the gain we show by an arrow. Okay. Then on this side you have b0 z inverse b1, then again z inverse b2, added together, that will give me y n. Okay. This is the direction flow of information, so not minus. Now, since these two elements are appearing from the same signal, I might as well club them together. This is delay of this output, basically it is here. This is the delay of this output, this is also delay of the same signal. So, these can be bridged and I need not have these two delay elements separately. So, for a biquad I need two delay elements. all right. So, the number of delay elements in this arrangement will be depending on the highest order of the polynomials either in the denominator or in the numerator. Okay. So, this is known as a canonic form, means requiring minimum number of delay elements. So, with this canonic structure in the earlier case, that is for step invariance, will require only one element. Let us take some examples for filter. Let us have a filter with these specifications. A Butterworth filter is to be designed with the specification that magnitude of H is less than equal to 1, on the other side it is 0.891. That means between 1 and 0.891, okay. And this is for 0 omega 0.2 pi, and H magnitude is less than equal to 0.17783 for omega between 0.3 pi to pi. Okay. That means from say 0.3 pi, suppose this is 0.3 pi up to pi, it should be within this value, less than 0.177. The specifications can be given in terms of absolute magnitude of the gain, sometimes in the logarithmic gain. Okay. So, by impulse invariance method, we are going to design this filter first. We can see in the impulse invariance there is a t coming there. So, t will get cancelled when we convert it, all right. So, we can take t equal to 1. So, we will put omega is equal to capital omega. So, these specifications we can write in terms of capital omega. So, 0.891 is H j omega all right, and H j omega is less than equal to 0.1778 in the, this is in the pass band, okay. That is omega less than 0.2 pi, and here 0.3 pi omega pi. So, H, this is in the continuous domain. So, I will write H c, okay. What was given was in the discrete domain. In the continuous domain, by putting omega equal to small omega equal to capital omega, we are going into the continuous domain. So, H continuous domain, the function is 1 plus omega by omega c to the power 2n. This is a Butterworth filter of nth order. Now, we have to compute, the two unknowns are omega c and n. So, you have to compute these two quantities with these specifications. There are two inequality constraints. So, if you equate these, that is, we are trying the border values. If you equate these two, then 0.891 squared, this is 0.89 squared is equal to 1 by 1 plus omega by omega c to the power 2n, where omega c is corresponding to 0.2 pi. Okay. The other way around, sorry, 0.2 pi by omega c is not, omega c is unknown. In the other case it is 0.1778 squared equal to 1 by 1 plus 0.3 pi by omega c to the power 2n. If you solve these two, you get n is equal to 5.88 and omega c equal to 0.704. Okay. So, we choose n is equal to 6, nearest integer. So, n is equal to 6 will give me the roots placed at an angle of 360 degrees divided by 2 into 6, 12. So, 30 degrees, all right. So, even number of roots, if you remember, we discussed earlier, even number of roots, 6 roots on this side. So, there will not be anything on the real axis. So, at 15 minus 15 degrees, 15 plus 30, 45 degrees minus 45 degrees, 45 plus 30, 75 degrees, then again 105, 15 degrees, 105 degrees, 135 degrees and so on. They are just mirror images. Okay. 1, 2, 3, 4. So, 1, 2, 3, 4, 5, 6, 6 on this side, 6 on the other side. So, you can form the polynomials. And what is the radius of the circle? It will be 0.704. No, it is the cutoff frequency now. It is normalized against this omega c. So, this is of radius omega c equal to 0.704. All right. So, you know the roots. Cosine of 15 degrees on this side, cosine of 15 degrees with a negative sign, and sine of 15 degrees and 45 degrees also, and so on. So, the polynomials, if you take the pair of roots at a time, you will get s squared plus 0.365 s plus 0.495 after denormalizing, s squared plus 0.995 s plus 0.495 into s squared plus 1.359 s plus 0.495. Okay. Now, for, if you remember, we had earlier discussed, if I have a function a by s plus a, its corresponding discrete domain representation is 1 minus e to the power minus at z inverse. Okay. All right. Then s plus a by s plus a whole squared plus b squared, exponentially decaying cosine function, corresponding z transform is t into 1 minus e to the power minus at cos of bt into z inverse divided by 1 minus 2 into e to the power minus at cos of bt into z inverse plus e to the power minus twice at z inverse squared. Is that all right? Similarly, b by s plus a whole squared plus b squared will give you t into e to the power minus at sin bt Z inverse, okay, divided by same denominator. All right. So, this we derived earlier. So, we will be making use of this, making partial fractions of this H s and then making substitution correspondingly. We shall get this as one minus e to the power minus a k cosine b k z inverse divided by 1 minus 2 into e to the power minus a k cosine b k z inverse plus e to the power minus twice a k z to the power minus 2, k varying from 1 to 3 into this is basically corresponding to s plus a k by s plus a k whole square plus b k square. So, corresponding to this term, this is the expansion. So, in this case, in this particular example, we have already got these 3 factors. So, after doing this kind of partial fraction and simplification, it reduces to 0.287 minus 0.447 z inverse divided by 1 minus 1.297 z inverse plus 0.695 z to the power minus 2 plus 3 such similar terms. I am not going to write all the details. Similar terms will appear for the 3 factors. There are 3 quadratics. So, there will be 3 such terms. Now, the same problem, if we go for bilinear transformation, let us see what will be the effect. Now, in case of bilinear transformation, we need pre-warping. All right. So, we change the specification for pre-warping. Let us see how we do that. The same magnitude 0.89125 should be h in the continuous domain j omega equal to 1 and h c, this is for the pass band 0 omega, and then what did you get in the bilinear transformation? What was the relation between discrete frequency omega and capital omega, small omega and capital omega? Tangent of omega t by 2, this capital omega into t by 2. Is that all right? So, if we normalize, if we take t to be 1, then 2 tan inverse or tangent? Are you sure? Are you sure? Tan inverse. So, omega into t is 2 into tan inverse omega t by 2. You mean this? Are you sure? Okay. So, we will apply these transformations, or you can write omega is equal to, it is the other way, no, t is not there. Yeah. So, it is omega is equal to 2 by t tangent omega by 2, all right. So, HC, so this specification should be 0 omega 2 by t tangent 0.2 pi by 2. Is that all right? Because omega is equal to this much. So, we are replacing that omega, limit of omega by this. Similarly, HC should be magnitude HC should be less than 0.17783 for 2 by t tangent 0.3 pi by 2 omega, then this is infinity. Earlier it was pi in the discrete domain, in the continuous domain it is infinity. So, if you use this 1 plus, let us convert this into equations, equality equations, 1 plus 2 tan 0.1 pi, this is 0.1 pi by omega c to the power 2n, that should be equal to 1 by 0.891 squared. Okay. This is h square, and the other one is 1 plus 2 tan 0.15 pi by omega c to the power 2n, should be 1 by 0.178 squared. Is that all right? T we have taken as 1, all right. Therefore, n, if you solve these two, n comes out to be 5.30466. So, we once again take the nearest integer n equal to 6. If we substitute in the first equation, then omega c becomes 0.766. Okay. Now, see, this is omega, this is small omega, all right. This is the kind of graph we are getting. As capital omega tends to infinity, this omega tends to pi by 2, pi, sorry. Okay. So, if I have a function specified like this, suppose this is a filter function specified, these frequencies will be marked here, this marked here. So, here it is much more compressed. Let me plot it. It is somewhat like this. Sorry, it will be within pi, because this entire infinite range is compressed within pi. So, it will be it will not go beyond this point. So, you can see there is a compression here. Okay. So, that is why while pre-warping we have expanded this, so that after compression it takes the normal shape. In any case it will get compressed here. So, while specifying we stretch it. If you stretch that, then it is better to take the first equation. First equation, n is more, to meet the same specification. If n is made more, that means omega c will also be more. This ratio has to be equated to the same constant, n is fixed. So, if you take higher values, then this gets stretched. So, that is going to aid the design. So, if you follow this, HCS comes out to be 0.20238 divided by S squared plus 0.396 S plus 0.5871, then S squared plus 1.083 S plus 0.5871 into S squared plus 1.4802 S plus 0.5871. Okay. You have got the three factors. Now, you are going to make a direct substitution. There is no partial fraction required. Unlike the earlier case, here you do not require any partial fraction, no substitution, no transformation in terms of impulse response. We make a direct substitution. S is equal to 2 by T and 1 minus Z inverse by 1 plus Z inverse, and since we have taken normalized T equal to 1. So, it will be just 2 into 1 minus Z inverse by 1 plus Z inverse. Okay. T has been taken to be 1. So, if you substitute that here, you get Hz, it is the discrete filter, as 0.000738 into 1 plus Z to the power minus 1 whole to the power 6 divided by, see, 1 plus Z to the power minus 1 squared, squared and squared. So, that gives me, it comes in the numerator as to the power 6. Here in the denominator you get 1 minus 1.268 Z to the power minus 1 plus 0.7051 Z to the power minus 2 into 1 minus 1.0106 Z to the power minus 1 plus 0.3583 Z to the power minus 2 into 1 minus 0.9044 Z to the power minus 1 plus 0.2155 Z to the power minus 2. So, you get 3 quadratics in Z square, Z to the power minus 1 and 1 plus Z to the power minus 1 to the power 6 in the numerator. So, the order is 6 in the numerator, 6 in the denominator. So, you require 6 delay elements. In the other one, in the impulse invariance, how many did you get? How many delay elements were there? There also you got 6, is not? There you have to put all of them in parallel mode. Sometimes the specifications are given in decibel gain. So, we may be given, say, Hs is equal to j omega, magnitude as in the pass band if the specifications are given in the pass band and stop band, we might as well write this in another form. Some people like to take the frequency in terms of omega p. Omega c is not known, so we are not going to try to find out omega c. We will straight away take omega p. Okay. So, we also define a loss function. Instead of gain, we define loss function, and that may be 1 plus epsilon squared omega by omega p to the power 2n. Basically, loss means in terms of power, so square of that 1 by Hs square. Hs is basically the output by input signal gain. So, power gain will be H j omega squared. So, loss will be in terms of in frequency domain is equal to j omega, it will be this much. So, epsilon is, and if this loss is expressed in the logarithmic domain, so a omega will be 10 log 1 plus epsilon squared into omega by omega p to the power 2n, so many dBs. All right. So, the loss function looks like this. I will come to this afterwards. Loss function looks like this. Within a certain band, this is the pass band, the loss, maximum loss that the filter can suffer is specified A max. All right. That means the gain should not fall below this point, that means the loss should not be above this. Similarly, in the stop band we want the loss should be at least this much, it should be above this. So, this is A minimum. So, A minimum is very high and A max is very small. Mind you, A max is not necessarily greater than A minimum, or never greater than A minimum. A minimum means in the stop band, this is the minimum loss it should have. So, it is a very high value. So, epsilon, if you are given this specification that in the pass band A max is the maximum loss, then 10 to the power 0.1 A max minus 1 under root will be epsilon from here itself. When omega is equal to omega p, that will become epsilon squared. So, A corresponds to A maximum. So, A max divided by 10. So, 0.1 A max. If you exponentiate with respect to the base 10, so 10 to the power this minus 1, that gives me epsilon. Okay. And let us work out one example. Find the loss at omega s is equal to 40 radians per second for a fifth order Butterworth filter. With maximum loss, that is A max, with the maximum loss A max equal to 1 dB in the pass band edge. This is the pass band edge frequency of 10 radians per second. That means you are given this is 10 radians per second, this is 40 radians per second, this is the maximum loss A max, and you have to determine the loss here. If this is of fifth order Butterworth polynomial. Okay. So, epsilon is root over of 10 to the power 0.1 A max minus 1. So, that gives me 10 to the power 0.1 and A max is given 1 dB. So, 0.1 into 1 minus 1. Is that all right? So, 10 to the power 0.1 is how much? If you take log 0.1 into log 10 is 1. So, 0.1 that is log of 5 minus log of 4 approximately. Log of 4 is 0.6, log of 5 is 0.7. So, the difference. So, 5 by 4 is 1.25. So, 1.25 minus 1.25. So, under root of that approximately 0.5. Okay. Under root of 0.25. So, omega s will be, what will be omega s? Stop band frequency 0.509 to the power 1 by 5 into 4. No? Basically, it is epsilon. Actually, this is 0.5 was an approximation. Actual value is 0.509. Okay. So, epsilon to the power 1 by n into whatever was that omega s by omega p, omega by omega p, okay, will be, no, this will be the normal omega. See, omega s was given as 40 radians. Okay. 40 radians. We have got epsilon. Yeah. So, if you can put in that equation, what was the equation? You can see the loss function was 10 log, okay, 1 plus, sorry, this is not, I was calculating something else. 1 plus epsilon squared omega s by omega p, and how much is that? Is equal to 4. So, 4 to the power 10. Okay. So, that is equal to 10. 1 can be neglected, 1 plus, and how much is epsilon squared? 0.25 into 4 to the power 10. So, that is approximately equal to 10 log 0.25 into 4 to the power 10. Okay. So, I can write 10 into log of 4 to the power 9. So, 90 log 4 is 0.6. So, approximately 54 dB. Okay. Okay, thank you. Now, in the design manuals, you may refer to design manuals where for different values of A maximum in a normalized frequency, omega p by omega s by omega p is known, Okay, you make a plot of omega by omega p, omega by omega p. So, omega p is taken as 1. You have for different orders n is equal to 1, 2, etc. You have such plots, and so this is between 0 and 1, and 1 to 10 next decade you have in the stop band you have the plots, because omega s will be given omega s by omega p, suppose the ratio is 4. So, I will go to 4, and for different values of n, as n increases it goes on increasing, all right. So, at n is equal to 4 I can read off that particular stop band dB, that is a minimum. If a minimum is specified, I will just refer to the nearest integer value, okay. I will go to the higher value next integer. So, I select n. Once you select n, the Butterworth polynomials are fixed, all right. They are all on the unit circle, you know the location of the roots. So, you can calculate the Butterworth polynomial, and even they are also available in the table. So, the design is very simple with the help of such charts for different values of A max. A max will have to be given. So, they give 0.25 dB, 1 dB, 0.5 dB and so on. So, these are specified and these curves are available. You can always select the particular value of n and design the filter. Okay, we will stop here for today. We will continue with this in the next class. Thank you very much.